The current real number system has no measure. The length of the interval a, b, is b minus a, which is very consistent with people's intuition. Extending the interval length to the measure of the set, Lebesgue established the measure theory. This is exactly what Lebesgue said: I wish first of all to attach to sets numbers that will be the analogues of their lengths. Here, Lebesgue regards the interval a, b as a set consisting of all rational and irrational numbers between a and b. We naturally ask, who is responsible for the length of the interval a, b? In other words, who is the mathematical undertaker of the measurement? There is a contradiction here. How does a number without a measure, with a measure of 0, constitute an interval with a measure? In order to conceal this contradiction, Lebesgue have to resort to the wrong infinite set theory, and describe the irrational number, or transcendental number, as the mathematical undertaker of measurement. Why are irrational numbers, or transcendental numbers, the mathematics undertaker of measurement? Answering this question directly will still fall into the aforementioned contradiction. However, with the help of infinite set theory, the method of elimination can be used to complete the proof process. The following is the main logic of the demonstration of this theory. The intervals and the line segments corresponding to the intervals have positive measure, and the measure of any algebraic number, and its corresponding point is 0. However, the interval, and its corresponding line segment, is composed of the algebraic numbers, and their corresponding points, and the transcendental numbers, and their corresponding points. Therefore, the transcendental numbers and their corresponding points are the mathematical holders of the measure. What is wrong with Lebesgue and others? In fact, the interval and its corresponding line segment are not composed by two kinds of things but composed by three kinds of things: the algebraic numbers, the transcendental numbers, and the blanks between numbers. It was ridiculous to arbitrarily assert that the transcendental numbers, and their corresponding points, were the mathematical holders of the measure when merely the algebraic numbers, and their corresponding points, were excluded because those mathematicians didn't know the existence of the blanks, which are as many as the real numbers. As a matter of fact, the real numbers have never filled up the number axis because the numbers and points in current theory have no size, whereas the number axis does. Blanks can always be found on the number axis no matter how many points without size there are. Any demonstration based on such assumption that points without size can fill up the entire axis is untenable. Numbers can't have measure while quantities can. The quantity is the difference of two numbers. When considering analytic geometry properties, there is no difference between points corresponding to algebraic numbers and points corresponding to transcendental numbers. Therefore, if the algebraic numbers are not the mathematical holders of the measure, then the transcendental numbers can't be the mathematical holders of the measure, either. If we examine the measure theory from another perspective, we can also find this theory untenable. The measure of one transcendental point, or number, is 0, and the measure of countably infinitely many transcendental points, or numbers, is 0, too. However, the measure of uncountably infinitely many transcendental points, or numbers, is a concrete number which isn't 0. Why is it so? Without any explanation, how can we accept this kind of logic, besides forcibly accepting it? Apart from the set of all real numbers, and the unbounded sets of real numbers, no number sets have uncountably infinitely many numbers. The set of the entire natural numbers is the proper subset of the set of the entire real numbers. Thus the one-to-one correspondence shouldn't be allowed be established between these two sets. However, the set of entire natural numbers isn't the proper subset of the bounded subinterval of the set of entire real numbers. Therefore, There aren't any correlations between these two sets, and the one-to-one correspondence can be established between the set of natural numbers and any bounded interval of real numbers. This is why any bounded interval of real numbers is countable.